How does the sun's energy come to Earth and warm us up? Light from the sun travels in waves and carries energy. Light acts as both a wave and a particle. It is made of photons, which are tiny massless particles of energy called electromagnetic radiation. You don't need to know this part, but if you're interested, there it is. The sun does provide some heat directly to the atmosphere, but much of the heating of the atmosphere comes indirectly from the sun through other means, as shown in the figure below and the figure to the right. In this image, I see that this entire band is representing the sun's light. And you can see that 23% is absorbed by the atmosphere. And by the atmosphere, they mean all of the gases that make up the atmosphere, including clouds. 48% of this light is absorbed at the surface. And this is what we saw when we collected our data, where surfaces absorb heat or warm up when they are placed underneath a light. And then about 29% of it is reflected. And in our simulation, when we saw the waves come in and hit the surface and then just bounce back out unchanged, that's an example of reflected light. You can also see more in this image, although it's a little bit more complicated. Again, it shows the incoming solar radiation. Some of it is reflected back into space before it adds any sort of thermal energy to our planet or the atmosphere. About 23% of it is absorbed by the atmosphere. 48% is absorbed at the surface, and then about 7% is reflected at the surface. So again, lots of information in this diagram right here. For light to directly provide heat to a substance, that substance must absorb the light. Absorbing light essentially means that the energy in the light causes the molecules of the substance to speed up. But why does light make molecules move faster? A more detailed answer requires fairly advanced physics. But for now, assume that there are discrete levels of energy to the motion of these particles, and also discrete amounts of energy that can be transferred. Discrete means a very specific amount. Therefore, for a substance to absorb light, the light must have the right amount of energy to push a molecule into faster vibration. These faster vibrations are felt as heat. This right here is a big idea. The faster molecules soon collide into neighboring molecules and pass along the energy, which causes the entire surface to warm up. Okay, so this is saying that molecules at the surface are getting energy from the light, which makes them vibrate faster. But then when they collide into neighboring molecules, they pass along the energy throughout the entire surface. So that's another big idea. Please pause this video and answer the question, how does light from the sun become heat on Earth? If light is absorbed, it does not pass through the substance, and the substance is opaque. Earth's surfaces, for example, are opaque because light is absorbed. It doesn't just pass through. In contrast, a substance is transparent when the energy of the light is unable to excite the molecule into moving faster, and instead the light passes through. Most gases in Earth's atmosphere are transparent to most wavelengths of incoming sunlight. This is why when we were looking at the simulation and the light waves were coming from the sun, they passed right through those carbon dioxide molecules as if they weren't even there. They didn't bounce back, they didn't change in any way, and the molecules of carbon dioxide also didn't change. They didn't vibrate faster, they didn't heat up, it all just stayed the same. They are transparent to most wavelengths of incoming sunlight. Some of the other parts of the atmosphere, including clouds, which are liquid water, water vapor or gaseous water. This means water that is a gas. We can sometimes call that steam. And certain compounds, for example, ozone, do absorb these wavelengths, totaling about 23% of incoming energy contained in sunlight. So again, it's not the air that's absorbing the energy from the sun. Rather, it is the primarily water that is in the air as either a cloud or a gas that is absorbing the incoming light energy. However, the rest of the sunlight reaches the surface of Earth. And you can look at the pictures above again if you want some more help with that. So why doesn't the sun directly heat most of the air? Please pause the video and answer this question. So, how does light heat Earth's surfaces? Going back a few sentences, recall that being opaque means that the light is absorbed. Since the ground and most other stuff on Earth's surface is opaque, this means that the remaining 77% of sunlight is absorbed at Earth's surface. Mostly, some is reflected, but the majority is absorbed. We learned that lighter substances will reflect more of the light than the darker surfaces. How does the air get heated? Some of the energy absorbed by Earth's surfaces heats and evaporates water, which then goes into the atmosphere. This might turn into a cloud, or it might just be water vapor in the air, which we call humidity. Those warmer molecules can bump into other molecules and particles in the atmosphere, increasing the temperature. Also, some air molecules come in contact with the warm surface and get energy directly from the ground, causing them to vibrate faster and feel warmer. In addition, some of the energy which is absorbed by the surface is re-emitted or given off from the ground as infrared light, a light not visible to humans with a different energy and a different wavelength. We saw that in our simulation. They looked kind of like a little line or a little worm. Some gases in the atmosphere do absorb infrared light and thereby capture another indirect portion of the energy which was in the incoming sunlight. Again, we saw that the carbon dioxide gas molecules in the air are able to absorb infrared radiation and thus heat up. What are the 3 ways that air gets heated? Explain. Pause the video and update your notes. How does this relate to the greenhouse effect, otherwise known as climate change? These particular gases, those carbon dioxide and water vapor, are known as greenhouse gases, and they are extremely important for keeping our planet a comfortable temperature. If we didn't have those gases, most of the infrared that would just go straight out into space and our planet wouldn't stay very warm during the day. You can see that right here in this image. However, too many of these gases in the atmosphere results in temperatures that are too high. And that is what we are seeing here, our human-enhanced greenhouse effect. We are all experiencing this.